Alright, so today we are covering semisimplicity of representations. It's a big chapter. Hopefully we can get through all of it in one video here. So we start out with a lemma. We're kind of going to push forward, hopefully try to go as quick as we can. Let G be a semi-simple Lie algebra. Then it states that the adjoint representation of G is semi-simple, and every ideal and quotient algebra is semi-simple. And well, let's look at the proof here. So we're going to pick an ideal in G, call it A. Then it's orthogonal, call it B of A in G with respect to the killing form. I still don't know if that's actually how you're supposed to pronounce it. It doesn't have a pronunciation guide in Wikipedia. Okay, this is an ideal of G, and intersection B is a commutative ideal. And by semisimplicity is 0. Hence B is supplementary to A in G. Moreover, also, since the killing form of G is non-degenerate, so are its restrictions to A and B. Hence A and B are semi-simple. And based on our previous results about products, that is everything. Now, go right into another lemma here. Let G be a Lie algebra, and the following are equivalent. First off, we have that all finite dimensional linear representation of G are semi-simple. B, given a linear representation rho of G on a finite dimensional vector space V, with a vector subspace W of codimension 1 such that row of x on V is in W for all x and g. So essentially, row reduces the vector space in which it acts by one dimension. Then there exists, I'll try to keep my abbreviations consistent. There exists a supplementary line of W, because it's codimension 1, which is stable under row G and hence is annihilated by it. Now proof. A implies B is automatic. What about B implies A? So we have B holding. Let sigma be a finite dimensional representation of G on a vector space M with a subspace, vector subspace of course, N, which is stable under row of G. We're going to let mu be the representation of G on the linear maps of M canonically derived from sigma This is that mu of x is equal to the adjoint in the linear maps on M of row of x. Let V be the subspace of Lm consisting of linear maps of M, which is all implied by our domain, into restriction of maps into N whose restriction to N is a homothety. And then and if V is W, this is going to be 0. Then W is of codimension 1 in V, and we have that mu x of V is in W as we wanted for all x in G. By condition B, there exists an element U in our V, which is annihilated by mu x for all x in G and whose restriction to n is a non-zero homothency. By scaling u, multiplying it by a scalar, we can assume u projects m onto n. So mu x of u equals 0 means u is permutable with sigma of x. Hence the kernel of u is a supplement of n in M, which is stable under sigma x for all x in G. Hence, sigma is semi-simple. Alright, well, now that we got that lemma done, let's look at another lemma. Let G be a semi-simple Lie algebra with a linear representation sigma on a finite dimensional vector space V with subspace W of codimension 1 such that rho x, this is the same setup as before, rho x of V is in W for all x in G. Then there exists a supplementary line of W stable under rho G. So this is basically like part B of before. Except that we have that G is semi-simple rather than all of its representations very similar. Something like that. I gotta maybe go over it a bit more detail after, but anyways, proof. For all x in G, let sigma x be the restriction of our given representation of x to W. That's not the order, you would write that in. The restriction of rho to W of x. Suppose first that sigma is simple. If it's 0, then rho x, rho y is equal to 0 for all x and y in G. Hence, rho G equals rho of the derived algebra of G is going to be 0. And we're done. If sigma is not 0, let n be the kernel of sigma with a supplementary ideal M in G. Then M is going to be non-zero, and the restriction of sigma to M is faithful. So sigma is going to be faithful on M, essentially. The restriction to M of the bilinear form associated with sigma is non-degenerate, and hence the Casimir element, remember that old lesson from a while ago, long ago, elements C of M and sigma exists. Therefore, by previous results, sigma of C is an automorphism of W. We also have that sigma C of V lies within W. Hence Z equal to the kernel of rho of the Casimir element of M and rho is a supplementary line of W, and since C belongs is in the developing algebra of G, the center of the developing algebra of G, we have that rho C permutes with rho X for all X in G, so Z is stable under rho G. In the general case, we use induction on the dimension of V. So we're going to let T be a minimal, not minimum, minimal, non-zero stable subspace of W. We're going to let rho prime be the quotient representation on V prime, which is equal to V divided by T. Then for all x in G, rho prime of x of V prime is within W prime, where of course W prime is equal to W over T, is codimension 1 in V prime. Now by the inductive hypothesis, there exists a line Z prime supplementary to W prime and stable under rho prime of G. Its inverse image Z and V is going to be stable under rho of G. It's going to contain T as a subspace of codimension 1. We have that its intersection with our original stable subspace is going to be equal to T, giving us that rho x of Z is inside of T for all x in G. From the previous paragraph, exists a supplementary line of T and Z stable under rho G. This is going to be supplementary to W in V. Okay, so how long has it been here? Okay, let's keep, we got lots of time. So let's go to another theorem. This one comes to us from Weil. It says every finite dimensional linear representation of a semi-simple Lie algebra is completely reducible. And the proof by the previous two lemmas. Alright, so now I'm going to move on to a definition here. I think this is a repeat. I'll go over it because it's minor. a Lie algebra G is simple if its only ideals are 0 and G, and G is non-commutative. I'm pretty sure we saw that way early on from a different book, maybe not, but it's here now again, just as a reminder in case. A Lie algebra proposition is that a Lie algebra G is semi-simple if and only if it is the product of simple algebras. And we've already shown that this condition on the right is sufficient to prove that it is necessary. Suppose G is semi-simple, we have that. Since the adjoint representation of G is semi-simple, G is the direct sum of minimal, non-zero ideals AI from 1 to m, then G is identified with, of course, the product algebra of these ideals. So then each AI is then an ideal of G and says every ideal, oh no, okay, never mind, I read this wrong. Each ideal of AI is ideal of G, and so is 0 or all of AI. Also, each AI is non-commutative. Hence, each AI is simple. Corollary. A semi-simple Lie algebra is the product of its simple ideals Gi, and which every ideal is the product of certain GI. So G is the product of AI for simple AI. As the center of each AI is 0, the centralizer in G of each AI is the product of AJ for J not equal to I. So we're going to let A and G an ideal. If it does not contain AI, then its intersection with AI must be 0. So its bracket with AI must be 0. And so we have that A must be inside this product of elements not containing, ideals not containing AI. This A is the product of certain AI and thus simple ideals of G are the AI. We note here that these simple ideals we have as above are called the simple components of G. Okay, now the corollary here. Now let G and G prime be Lie algebras. With radicals R and R prime and a homomorphism F from G onto G prime. And then we have that the radical G prime is F of R. I think this homomorphism is surjective. Maybe not. It says onto. Anyways, proof as f of r is solvable, f of r must be contained within r prime. As g over r is semi-simple, then g prime over f of r is semi-simple as semisimple being isomorphic to a quotient of G over R, so maybe homomorphism isn't subjective. Hence, FR also contains R prime. All right. So, we have a couple remarks which follow this. Weil's theorem admits a converse. If every finite dimensional representation of G is semisimple, so is G. And let's go ahead and show that as the adjoint representation is semisimple. Every ideal of G admits a supplementary ideal and hence can be considered a quotient of G. If G is not semisimple, G admits a non-zero commutative quotient and therefore a quotient of dimension 1. And the Lie algebra K of dimension 1 admits non-semisimple representations. For example, the map sending element lambda to this matrix on R2. So, if every finite dimensional representation is semisimple, then G has to be semisimple. Remark number 2. Let G be a Lie algebra over K with sigma a representation on of G on a vector space M. We're also going to let FB, a k-linear mapping of G into M such that f of the bracket of x and y is equal to sigma x on f of y minus sigma of y on f of x for all x, y in G. Now, from a previous result, being given sigma f is equivalent to being given a homomorphism x into the pair of fx and sigma x, of G into the affine Lie algebra of M. We have also seen that fx sigma x of the affine x is canonically identified with the element rho x of the general linear Lie algebra of N, which is N is M times K. Which induces sigma x on M and maps 0, 1 of N to f of x. We also have that rho is then a representation of G on N such that rho of x of N is in M for all x in G. If G is semi-simple, there exists a line Z supplementary to M in N, which is also annihilated by rho of G. So that there exists an element MO of M such that negative MO, comma 1 in N is annihilated by rho of x such that f of x is equal to sigma of x acting on MO for all x in G. Oh, I think we made it to the chapter actually. Yeah, that's our next thing there because there is a side point, I guess, which no, let's go through a side point. Just for the sake of it, just for the sake of completeness, learning as much as we can. Remark 2 prime. Suppose that k is now equal to the real numbers. We're going to let capital G be a connected Lie group with Lie algebra G. Consider an analytic homomorphism phi of G into the affine group A of M corresponding to a homomorphism x to, of course, fx comma sigma x of G into the affine Lie algebra of M. Then 2 is interpreted, so this is the group analog, as if G is semi-simple. Then our analog phi of G leaves a point of M fixed. Let's go into that. Let H be the elements of the general linear Lie group of N, leaving stable, which leaves stable all the linear varieties of N parallel to N to M. There exists a canonical isomorphism psi of A onto H. We're going to let Z be a supplementary line of M in N. Saying rho of G annihilates Z amounts to saying that the composition of psi on phi on G leaves the points of Z fixed, and hence that phi of G leaves fixed the projection onto M of the point of intersection of Z and the product of M and 1. And now we are officially done everything for this chapter. I had to push really hard, like try to get fast, and we're still like at 50 minutes, but you know, I think we got some good stuff out of it.